In the first part of today's experiment, we are going to be studying the case of ohmic devices. We saw before that for an ohmic device, the relationship between the voltage and the current is actually a straight line relationship, which is an indication that not only the voltage and the current are directly proportional to each other, but also it's an indication that the slope in that case, which is none other but the resistance, is a constant for an ohmic device. It's always a constant for an ohmic device. For that matter, on that circuit board over here, we are going to be studying the behavior of a 10 ohm resistor. So that first terminal over here, it corresponds to a resistor of 10 ohm, which we are going to connect to the output of a power source. So over there on that interface, we have these two terminals. We have the ground terminal and the positive terminal, which are terminals of a power source, the terminals of the output of a power source. So we are going to bring one connection from one output and plug it into that 10 ohm resistor, and then over here we have a common terminal in that circuit board. So that terminal is basically a common terminal from which we are going to take out an electrical wire and we are going to branch it into the ground terminal over there. Now over here we are going to click on Ohm's Law folder. We are going to choose the ohmic device folder, and then over here we are going to click on start, and then we click on stop. So now we have collected data for the voltage versus the current. So now we have data for the voltage which is being applied to that resistor, and the values for the current which is flowing through that resistor. And as we can see, the relationship between the voltage and the current is actually a straight line relationship, which is validating the fact that a resistor is an ohmic device. Now what we need to do next, over here we are going to click on that cursor, which is the XY coordinates cursor, and then we are going to be sliding these XY coordinates across the straight line in order to pick 4 different points for the voltage and the corresponding current. So over here the first value would correspond to X, which is the value of the current, and the second value would correspond to the value of Y, which is the voltage. So you are going to be sliding in an arbitrary manner that XY coordinate across that straight line, and you are going to be picking 4 different points for the voltage and the current. So on the report over here, for the first resistor, R equal to 10 ohms, over here you are going to fill in the values for the voltage. So here we have a mistake. That should be the value for the voltage and not the current. Over here you fill in the values for the voltage, and over here the corresponding values for the current. After doing so, they ask you to apply linear regression in order to determine the slope of the voltage versus the current, meaning that the voltage would be the Y variable and the current would be the X variable. And according to Ohm's law, which states that the voltage is equal to I times R, therefore the slope in that case would be none other but the resistance. So once you find the slope, that would imply that you have already determined the value for the resistance, which should be close or should be equal to that theoretical value which is given over here. Now after finding the value for the slope and therefore the value for the resistance, they also ask you to determine the error on that slope. So by applying the equation which corresponds to the error on slope, which is square root of n over n minus 2 summation of I squared over delta, you would be able to determine the error on that slope. Now for the second part, they ask you to repeat the same thing all over again, but now for a resistor of 33 ohm. So in that case, you are going to remove that connecting wire from the 10 ohm resistor and you are going to plug it into the 33 ohm resistor. And all over again, over here you are going to click on experiment, delete all data runs. So we are deleting any previous run, and then you click on start and you click on stop. And as we can see over here, now we have multiple values for the voltage which is being applied to that 33 ohm resistor, and multiple values for the current which is flowing through that resistor. And as we can see, the relationship between them is a straight line relationship. In a similar manner, we are going to bring that XY coordinate delta tool and we are going to slide it across that straight line in order to pick 4 different points for the current and their corresponding values of the voltage. That would be for the first part. Now for the second part, you are validating over here that even if you have resistors in combinations, and not only individually, but rather if they are in parallel or in series, you are still going to get an ohmic device for that combination of resistors. So in that part over here, they ask you to find or to connect the resistors in series and to find several values for their current and several values for that voltage. But over here you have to keep in mind that first off you need to find the nominal value for R equivalent when R1 and R2 are connected in series. So over here you find the theoretical value, which is the nominal R equivalent, and then after finding the experimental value later on you can compare them to each other. So for R1 and R2 to be in series, we are going to bring that connection, we are going to take it out of that common terminal and we are going to plug it into the 10 ohm resistor. So now we have the 10 ohm and the 33 ohm being connected in series. And over here again we click on experiment, delete all data runs, and then we click on start and we click on stop. So as we can see, the relationship between them is still a linear relationship, which is an indication that we still have an ohmic device over here. And in a similar manner, you are going over here to slide that XY coordinate delta tool across that straight line in order to pick 4 different points for the voltage and the current, for which you are going to apply all over again linear regression in order to find their slope and the error on slope. And then in that same part over here, they ask you now to connect both resistors in parallel, but first off, you need to find their nominal equivalent resistance. So over here, we are going to bring that connection. We are going to plug it in the 10 ohm resistor, and the other end of that connection, we are going to plug it into the 33 ohm resistor. So now we have the 10 ohm and the 33 ohm being connected in parallel. Now we need to connect them to the power interface or to the output of the power source. So we bring one connection from the positive terminal and we connect it over here, and another connection from the ground and we connect it into that common terminal on that circuit board. So now we have R1 and R2 in parallel and they are connected to the output of that power supply. Now over here, you click on experiment, delete all data runs, you click on start, you click on stop again, and as you can see, the relationship between the voltage and the current is still a straight line relationship, indicating that whatever combination that you have for the resistors, a resistor is always going to act as an ohmic device. So in a similar manner, you pick 4 different points for the voltage and the current, and then you apply linear regression in order to solve for the slope and the error on slope. And later on, you compare the value that you obtained for slope for the nominal R equivalent that you have obtained for 10 ohm and 33 ohm being connected in parallel. That would be for the second part of the experiment. Now moving on to the third part of the experiment, in which we are going to be studying the case of a non-ohmic device. We know that for a non-ohmic device, the relationship between the voltage and the current is not a straight line relationship, but rather it has a curvilinear shape. So in that case, the resistance for a non-ohmic device is no longer a constant, but rather it varies with the voltage and the current. For that matter, we are going to be studying the following light bulb in order to study a non-ohmic device. So you are going to be studying how the voltage and the current is going to be changing across that light bulb, and the relationship between them is going to be forming a curvilinear shape. So they ask you in that part to connect the light bulb in series with a 10 ohm resistor, and both being connected to the output of that power supply. However, if we look over here, we can clearly see that that connection is actually isolated from the outer connection. So we don't have any connection between the light bulb and that outer circuit. For that matter, we are going to bring that connection from the terminal and we are going to plug it into the common terminal on the outer circuit. So in that case, now we have connected the light bulb to that outer circuit. Then we are going to bring one connection from the output, from the ground terminal of that power source. We are going to plug it into the 10 ohm resistor, and then the second connection we are going to plug it into that terminal over here, which is on the same side of that light bulb. So now we have the light bulb and the 10 ohm resistor being connected in series. Now there is still one thing left to do. Over here our interest is only in studying the voltage and the current change across the light bulb. For that matter, we are going to bring a voltage sensor, and that voltage sensor is going to be connected across the terminals of that light bulb. So Over here we have the following connection, which is none other but the voltage sensor. That voltage sensor is going to be connected in channel A on that interface, and then these two plugs are going to go into the terminals that are surrounding that light bulb. So over here these two wires are going to be connected into the terminals across that light bulb in order to study solely the voltage change across that light bulb. Then over here we are going to close the ohmic device folder, and we are going to open the light bulb folder. And then you click on start, and you wait until the graph is done forming, and then you click on stop. Now, from that graph, now if we keep the graph that way, we are not going to be observing anything. As we can see from afar, it looks like it's a straight line relationship, but rather it's not. So let's try and enlarge it. So over here we are going to be changing a little bit the scales of that graph in order to render it more visible. And then over here we are going to zoom it out. So as we can see over here, we have a curvilinear relationship between the voltage and the current, which is an indication that a light bulb is a non-ohmic device. And in a similar manner to what we have done before, over here you are going to click on that XY coordinate delta tool, and you are going to pick 4 different points for the voltage and the current, 4 arbitrary points for the voltage and the current. And for each value of X and Y, you are going to be determining R, which is the resistance. So we know by Ohm's law that V equal to IR, so R would be equal to V over I. So by determining each value of the resistance, you would be validating that for a light bulb, the resistance is not a constant, but rather it's going to be varying from one point to another, which is an indication that the light bulb over here is a non-ohmic device. Now there is a tricky characteristic regarding that light bulb. That light bulb, it can either behave as an ohmic device, as we have seen over here, or it can also behave as an ohmic device for a certain frequency applied. Meaning that if the frequency applied to that light bulb is a very minimal frequency, therefore that light bulb would be behaving as a non-ohmic device, and if the frequency applied is a high frequency, therefore that light bulb would turn into an ohmic device, and therefore we have a steady value for the resistance, and we have a linear relationship between the voltage and the current. But how can the frequency in that case relate to the nature of that light bulb? How can the frequency turn that light bulb from a non-ohmic device into an ohmic device? The frequency, if you have a voltage with 0 frequency, that implies that you have a steady voltage, a direct current voltage. So any voltage with 0 frequency, it implies that you have a direct current voltage. But the frequency in that case is defined as what? The frequency is defined as the number of cycles that a voltage waveform would repeat itself per second. So for example, if you have over here a certain voltage at 0 frequency, that implies that we have a steady voltage and we don't have a sinusoidal waveform for that voltage. However, if we have, let's say, a voltage at 40 Hertz, what do we mean by that? A voltage at 40 Hertz. Let's say now we have more specifically 5 volts at 40 Hertz. So what can we infer from that? When we say that we have 5 volts at 40 Hertz, that implies that the 5 volts is actually repeating itself, or the waveform for that 5 volts is actually repeating itself 40 times per second. So let's say the voltage is starting over here at 0, then it goes up to its maximum value, which is 5 volts, then it goes down to 0 again, and it keeps going down until it reaches now minus 5 volts. So over here we have a crest and trough, which consists of the maximum value of the voltage and the minimum value of the voltage, which is a -1. then the voltage goes back up again until it reaches 0. So over here, that entire cycle, that entire waveform, it corresponds to one cycle for the voltage. So that entire waveform, it corresponds to one cycle. So when we say that we have a voltage of 5 volts being applied at 40 hertz, meaning that that entire cycle is actually repeating itself 40 times per second. So that entire cycle, it keeps being applied to whatever electrical component that you have, it keeps being applied to it at a rate of 40 times per second. So in the case, over here in that part, if you look over here, the frequency that was, the frequency at which that voltage was applied, it was about 0.1 hertz. So we were applying a voltage of 2.5, which has an amplitude of 2.5, and it was being applied to that light bulb at 0.1 hertz, which is a very minimal frequency. So how can the frequency in that case affect the nature or the behavior of the light bulb? If you have a low frequency being applied to that light bulb, therefore that voltage is being applied in a very interrupted manner. So in that case, the light bulb, which consists of a filament, of a tungsten filament, as we have seen before, it's not going to reach its maximum operating temperature. So it's not going to get hot enough in order to reach its maximum operating temperature, for which that light bulb would be constantly glowing in a white light. But rather that light bulb is going to be flickering on and off. So for a low frequency, you are going to have a change in temperature, a constant change in temperature. And if we have a constant change in temperature, therefore the resistance of that light bulb is going to keep varying, as we have seen before, as we have seen during the theoretical part explanation. So the temperature and the resistance, they are related to each other. So if the temperature is going to keep fluctuating, therefore the resistance is going to keep fluctuating as well. And in that case, we have a non-ohmic device. So at low frequency, we don't have a steady voltage being repetitively applied to that light bulb in order to render it hot enough, in order for it to reach its maximum operating temperature and stabilize. Therefore, the temperature is going to keep fluctuating, and the corresponding resistance would fluctuate as well, which is going to lead to having a non-ohmic device, which is characterized by that curvilinear shape over here. So over here, if we have a look, as we can see, we have a certain amplitude of 2.5 volts being applied at a certain frequency of 0.1 hertz, which is a very minimal frequency. It's not a frequency high enough in order to apply the voltage at a steady rate, in order for the temperature of that filament to increase and reach its maximum operating temperature. So if we have a look over here, if you can see that light bulb is actually turning on and off. If you have a look at it, now you can see it, it's slowly turning on and off, which is an indication that that voltage of 2.5 volts is actually being applied at a very minimal rate, at a very slow rate. And in that case, that light bulb is not getting heated enough, it's not being supplied with voltage enough in order for it to reach its maximum operating temperature, for which it would be glowing constantly in a white light. So in that case, let's say that over here we are going to increment that frequency up to 10. So now we are going to be applying that 2.5 amplitude at a certain frequency of 10 hertz, meaning that that waveform of 2.5 is being applied now 10 times per second. But moreover, we are going also to increment the amount of amplitude from 2.5 to 5 volts. So now in that case, if we have a look at that light bulb, now we can see that now the light bulb is constantly glowing. However, the light which is being given off by that light bulb is actually flickering on and off, but in a very rapid manner. So that's an indication that the light bulb, it didn't reach its maximum operating temperature yet at 10 hertz, but rather the frequency, it needs to be incremented furthermore in order for that flickering to be gone, and therefore in order for the light bulb to reach its maximum operating temperature, for which it would be constantly glowing. So let's say now we increment the frequency up to 20. So as we can see over here, the flickering now is almost gone. So now the light bulb is giving off a constant light. So the flickering is gone simply by incrementing the frequency of the voltage waveform that was being applied on that light bulb. So now what do you think would happen for that relationship between the voltage and the current at high frequency? So over here now we are going to be plotting the relationship between the voltage and the current at a certain frequency of 20 Hertz to see if anything is going to change regarding the nature of that light bulb. So by clicking on start and then clicking on stop, we have over here the formation of a straight line. So as we can see over here, we have a straight line relationship between the voltage and the current, which is an indication that now the nature of the light bulb is no longer a non-ohmic device, but rather it turned from being, or it transitioned from being a non-ohmic device into an ohmic device at high frequency. So that first graph over here that we obtained, which was a curvilinear graph, it was obtained at very low frequency for the light bulb, and we saw that at very low frequency the light bulb was flickering on and off, and this is due to the fact that the temperature which is reached by the light bulb, it wasn't enough temperature for the light bulb to stabilize, or for the resistance of that light bulb to stabilize. So in that case, by incrementing the frequency from 0.1 up to 20 Hertz, as we can see over here, first off, the light bulb, it stopped flickering, meaning that the temperature of the light bulb became steady at a very high frequency, and therefore the corresponding resistance of the light bulb also became steady, which has led to the formation of that straight line relationship between the voltage and the current, and therefore turning the light bulb into an ohmic device. Now moving on to the last part, in which you are going to be determining the resistivity of two different rods, of a copper rod and of an aluminum rod. We know that resistivity is basically an intrinsic property of a material, meaning it varies from one material to another. And resistivity in that case, it gives rise to impedance which is resistance. So the basic component for resistance would be the resistivity. So for the first part, they ask you to connect in series the copper rod with that power supply and with an ammeter. So the ammeter, the copper rod, and the power supply, they are going to be connected in series. So for that matter, we are going to bring one connection from the ground or from the negative terminal over here, and we are going to connect it to one end of that rod. So on both sides of that rod, we have actually two different ports. So we are going to be connecting one port to one end of the rod, and then we bring a connection from the other end of that rod, and we connect it over here to the COM on that ammeter. So that connection, it goes into the COM on that ammeter. Then we bring in another connection from the amps port, and then we plug it over here into the positive terminal on that power supply. So now, as you can see over here, we have the power source being connected in series with that rod, and then that rod is connected in series with that ammeter, which in turn is connected into that power supply. Now what we need to do next is we need to have measurements for the voltage or for the potential difference that is being applied to that rod. However, the value for the potential difference that we are going to read, it's going to be very minimal. The potential difference across that rod is going to be very minimal, and we need to amplify it, or we need to magnify it. So in order to amplify the value for that voltage within that rod, we are going to be using the following voltage amplifier. So that amplifier over here, basically, it magnifies whatever value that you are reading for the voltage. It doesn't add to it, it doesn't add an extra voltage to it, but rather it magnifies the value. So for example, if you are reading a certain value of 0.2 millivolt, and you are using a certain amplification of 10 to power 2, therefore that value of 0.2 millivolt would be multiplied by 100. So you would be magnifying it 100 times. So it's not like you are adding an external voltage to the already existing voltage, but rather you are magnifying the voltage that you are reading. So in that case, over here on that rod, as we can see, we have two different sockets or two different ports. We are going to bring one connection from the first socket, and we are going to plug it over here. So basically what we are doing is we are transferring whatever reading that we are, or whatever value that we are reading for the voltage, we are transferring it into that amplifier, and then we bring in another connection from the other socket and we plug it into the ground terminal. So over here what we are basically doing is we are transitioning, or we are transferring whatever value for the voltage difference that we are reading into that amplifier in order to amplify it. Now what's left is to find a value for that amplified voltage. So to find the value for that amplified voltage, we are going to bring a voltmeter. We are going to connect that plug over here to the voltage port on that multimeter, and then another connection from the ground terminal, and we connect it over here across the COM port on that multimeter. So now we have the multimeter or the voltmeter being connected to that amplifier in order to get a value for that magnified voltage. And over here, if you look closely, you can see that we are actually amplifying the voltage by 10 to power 3. So we are magnifying it 1,000 times. So let's turn on the power supplies. So after turning on the power supply and the amplifier over here, we are going also to turn on that ammeter, and the voltmeter is already turned on. Alright, so now what we are going to do next, if we have a look at that lab report, over here they are asking you to vary with the amount of current applied and to record the corresponding amount of voltage. So on that power supply over here, you have that following knob, which is for the voltage. We are going to be varying with the voltage that is, with the current that is being applied. It's not reading it, so we are going to switch to milliamps. Alright, so we had to switch the ammeters because the first one, it wasn't functional. So as I have told you before, over here what you are going to do is you are going to be varying the amount of current that is flowing through that rod, and then you are going to be recording the corresponding value for the voltage. Now over here, if you are reading a minus sign, that would imply that one of the connections is actually flipped and you need to switch it. So for example, if we switch these two connections, so now as we can see, now we are reading a positive value all over again for the voltage. So it's only a matter of connections. So whenever you vary the amount of current, you are going to be recording the value for the voltage. And as you can see over here, the value that we are reading for the voltage is too minimal, 0.024 volts. And this is why we actually used an amplifier in order to magnify the value for the voltage that you are reading or that is being applied to that copper rod. However, you have to keep one thing in mind, that over here, let's say in the first box or in the first row, we are recording a value for the current of 2.75 amps. However, over here, we are not going to be recording a value of 0.024 volts for the voltage, because if we go back over here, we are actually magnifying the voltage by 10 to power 3. So over here, we are only magnifying the voltage and we are not tampering with the intensity or with the current. Therefore, you are going to be dividing that value that you are reading over here by 10 to power 3. So in that first row over here, let's say you are recording a certain value for the current of 2.75 amps. Over here for the voltage, the value is going to be 0.024 volts multiplied by 10 to the negative 3. So basically over here we are removing the effect of that amplifier, since only the values for the voltage were amplified and not the values for the current. So in order to keep both values proportional to each other, we have to remove that margin of amplification that was imposed by the amplifier by actually multiplying each value by 10 to the negative 3. And the same thing for the second trial. So for the second trial, let's say that over here now we incremented the current up to 3.57. Now we have a certain value for the voltage of 0.034. All over again, you are going to be multiplying that value of the voltage by 10 to the negative 3 in order to remove the effect of the amplification. Now after you carry on, after you fill that entire table, now they ask you over here to apply linear regression in order to find the resistance of that copper rod. So how can you find the resistance in that case? So when you apply linear regression, and even when you draw the voltage versus current curve, or the voltage versus current plot, you are going to see that the relationship between them is a linear relationship. Meaning that copper rod over here is basically an ohmic device. So since we have a linear relationship between the voltage and the current, therefore we have an ohmic device over here. So when you apply linear regression, you are going to be obtaining a value for slope. That value of slope is going to be none other but the resistance. So V is equal to IR by Ohm's law. Therefore, the value for the resistance would be none other but slope. So you determined over here the value for slope and the error on it. Now in part number 3, they ask you to calculate the experimental resistivity for that copper rod. How can you calculate it in that case? We know that the resistance is related to the resistivity by R equal rho L over A. So in the previous part over here, in part number 2, you have determined the resistance of that copper rod by applying linear regression and using Ohm's law equation. V equal IR, you find the slope of the voltage versus the current, therefore the slope would be the resistance. So now over here you have a value for the resistance for that copper rod. The length would be none other but the length of that copper rod, so you measure it. So since you are measuring the length using a ruler, therefore there's going to be a certain amount of error on that length, which is none other but half of the least subdivision, 0.1 centimeter over 2. Now A over here would be the cross-sectional area of that copper rod. How can you find the cross-sectional area in that case? To find the cross-sectional area, you are going to bring the vernier caliper. So over here we have the following vernier caliper. First off, in order to be safe, we are going to disconnect that copper rod. Then we are going to bring in the vernier caliper, and you are going to be basically measuring. So basically over here you are going to be measuring the diameter of that copper rod. Once you measure the diameter, you are going to get a certain value for the radius. So as we can see over here, if we look at that vernier caliper, we have a leading digit of 20, which is in a millimeter. The unit over here, it's in millimeter, yes. So we have 20 millimeter, and leading digit is 20. And in order to figure out the subdivisions or the decimals, you are going to look at that 0 below is basically in front of which division. So the 0 is basically in front of 0.5. So over here we have a total length of, or a total diameter of 25 millimeter, which is basically 2.5 centimeters. So over here we have a diameter of 2.5 centimeters for the copper rod. So having the diameter, therefore the cross-sectional area is going to be A equal to pi r squared, and since the area was determined manually, therefore we have an error on the area, which is going to be also the least subdivision, 0.1 centimeter over 2. So now we have determined these parameters. Therefore the resistivity in that case would be what? The resistivity would be the resistance times the area over the length, and you find a certain value for the resistivity. Now they also ask you to find an error on the resistivity. What would be the error in that case? So as we have seen now, on the resistance we have an error determined previously using the linear regression method. On the area we also have an error, which is propagation of error, similar to the one that you have determined during the capacitance experiment. So over here you have to apply the propagation of error in order to find the error on the area. And then over here we have a certain error on that length. Therefore, the error on the resistivity would be what? Would be the derivative of the resistivity with respect to R, to the area, and to the length. So over here we have the first partial derivative with respect to length times the error on the length squared, plus a second partial derivative with respect to area times the error on area squared, and a third partial derivative of rho with respect to slope times the error on slope squared. And that would be for that part regarding the error on the resistivity, which is determined by using the propagation of error. And that would be it regarding our experiment of today.